Okay, welcome back to MacNab Chemistry. Today we're going to have a look at periodicity, i.e. how elements are arranged on the periodic table, and then we'll have a look at some of the physical properties of the period 3 elements. Okay, so to start with, let's have a look to see how elements are arranged on the periodic table. Okay, well, the first thing that you need to be able to do is you need to be able to write your electron configurations for each element, and then once you've done this, you can see where the outer electrons lie in that configuration. So for example, if I take the element lithium, its electron arrangement is 1s2, 2s1. Okay, so the outermost electrons are in a 2s1 suborbital, 2s1. So therefore we classify lithium as an s block element. If I take the element chlorine, its electron arrangement is 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so its outermost electrons are in a 3p, p suborbital, therefore we classify this as a p block element. If I take the element cobalt, its electron arrangement is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. So its outermost electrons this time are in the d subshell. Okay, so this is a d block element. Okay, so we classify elements on the periodic table into s, p and d block elements depending on where their outermost electrons lie, in which suborbital they lie. So lithium, the outermost electrons lie in a 2s1 suborbital, therefore it's an s block element. Chlorine, its outermost electrons lie in a 3p suborbital, therefore it is a p block element. Cobalt, its outermost electrons lie in a 3d suborbital, therefore it is a d block element. Okay, and then if I introduce the periodic table here like this, okay, you can see there that all the elements that lie in this part of the periodic table, they're S block, they're my D block, and they are my P block. And we don't need to worry too much about the F block elements at A level. Okay. Right, so now let's have a look at the physical properties of period 3 elements. Okay, the three physical properties we're going to look at are atomic radius, melting point and first ionization energy. Let's move that down a little bit. There we go. Atomic radius, melting point and first ionization energy. Okay, so let's first of all look at atomic radius. Okay, so atomic radius. So as we go across the period, the nuclear charge increases without any significant additional shielding. So as we go across the period in the periodic table, okay, if we look at this little diagram here, this little graph, okay, if I go from sodium to magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, as I go across my period, every time I go to the next element I have greater nuclear charge because I have an additional proton, but I'm still filling the same electron shell. Okay, so if my nuclear charge increases without any additional electron shells, i.e. without any additional shielding, then my atomic radius is going to decrease as I go across the period, because the force of attraction between the nucleus and the outermost electrons will get stronger as we go across the period. Okay, let's have a look at melting point now. Okay, right, okay, so if we look at our graph here, we can see that the melting points of period 3 elements changes depending on what they are and what type of element they are, whether they're metallic or non-metallic. Okay, so melting points, the change in types of melting point in an element changes its melting point. Okay, so the type of bonding it has changed its melting point. Okay, and I'd like us all to remember that metallic bonding exists because there is an attraction between the nucleus of the metal atom, okay, so between the nuclei of metal atoms and the delocalized electrons, okay, the outer shell electrons. Okay, so if we look at melting points, then we have to consider, right, what type of element is it? So sodium is a metal, so sodium experiences metallic bonding. Okay, so that's an attraction between the positive nucleus and its outermost electrons, or outer shell electrons. Magnesium is a metal, so again it experiences metallic bonding. Aluminium is a metal, therefore it shows metallic bonding. Silicon is a non-metal and it forms a macromolecular structure, and this is why we have such a high melting point here. So silicon has a macromolecular structure, therefore we have a very high melting point here. Then we get onto our smaller molecules, okay, so phosphorus, sulfur and chlorine, those are smaller molecules, okay, they are molecular. However, phosphorus takes up the structure of P4, sulfur takes up the molecular structure of S8, and chlorine takes up the molecular structure of Cl2. Okay, so phosphorus is P4, sulfur is S8, chlorine is Cl2. Well, P4 is clearly a smaller molecule than S8, which is a much bigger molecule than Cl2. Okay, right, so this trend, this pattern in size of the molecules is reflected by their melting points. So P4, it's smaller than S8, so it has a lower melting point, but P4 is bigger than Cl2, therefore P4 has a higher melting point. Okay, S8 is the biggest molecule, so that has the highest melting point of the three. Okay, this increase in melting point, or the change in melting point in these three molecules, is purely dependent on its size. The larger the molecule, the larger the van der Waals forces, or the stronger the van der Waals forces exist between the bigger molecules. So the bigger the molecule, the stronger the van der Waals force. S8 is very clearly the biggest molecule, therefore we have stronger van der Waals forces, i.e. temporary induced dipole-dipole interactions between the S8 molecules, therefore it has the highest melting point. Finally then, let's have a look at the first ionization energies as we go across period 3. Okay, first of all then, we need to remember what first ionization energy is. So first ionization energy is the enthalpy change for the removal of 1 mole of electrons from 1 mole of atoms in their gaseous state. Okay, so first ionization energies generally increase across period 3, and for that matter any other period. So what you understand about period 3 you can apply to other periods. Okay, so the reason that you get a general increase in first ionization energies across period 3, just get this focused a little better, I think. Yeah, there we are, it's a bit better. Okay, so let's go back to that. So first ionization energies generally increase across period 3, and the reason for this is, as you go across period 3, the nuclear charge increases. So we've talked about that already. As you go across period 3, the nuclear charge increases. But whilst you're going across period 3, there isn't a significant increase in the shielding of the positive nucleus for the outer shell electron. Okay, so we've got an increase in nuclear charge without any additional shielding. Therefore, more energy is required to break the bond between the nucleus and the outermost electron. Therefore, the first ionization energy across period 3 generally increases. Okay, so those are the general rules. However, there are a few anomalies. So let's have a little look at this here. There we go. we can see that, can't we? Yeah. Okay, so we've got first ionisation energy on my y-axis, and I've got my elements along the bottom there. So as you can see, there's a general increase in first ionisation energy as you go across period 3 from sodium to argon. However, you can see that there are a few anomalies here. Okay, so the first ionisation energy of magnesium is higher than that than sodium. However, when I go to aluminium, aluminium has a slightly lower first ionisation energy than magnesium. Okay, so to understand this, what we have to do is we have to look at the electron configuration. So magnesium has the electron configuration 1s2, 2s2, 2p6, 3s2. Aluminium has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p1. So in aluminium, my outermost electron, i.e. the electron that will be lost when aluminium forms the Al plus ion, i.e. when it loses one electron. Okay, so the aluminium's outermost electron is in a 3p subshell, which that electron there is more shielded from the aluminium nucleus than one electron trying to be removed from a 3s2 subshell in magnesium. Okay, so the reason that aluminium has a slightly lower first ionisation energy than magnesium is that in aluminium its outermost electron is in a 3p1 subshell. Okay, now let's have a look at phosphorus and sulfur. Again, the general trend across this period is that the first ionisation energy increases, but as we go from phosphorus to sulfur, you can see that the sulfur first ionisation energy is slightly lower than that of phosphorus. Okay, so again, we're going to have a look at the electron configuration of the elements and see where that outermost electron is being removed from, i.e. from which subshell it's being removed from. So let's look at phosphorus. The electron configuration 1s2, 2s2, 2p6, 3s2, 3p3. Okay, and these are my 3p subshells. So I'll go, and I've got 3 electrons, 1, 2, 3, like that. In sulfur, my electron arrangement is 1s2, 2s2, 2p6, 3s2, 3p4. Okay, so that's my 3p3 in the phosphorus. This one here is my 3p4 in the sulfur. So 1, 2, 3, and then the fourth electron pairs up like this. Okay, so remember, first ionisation energy is the energy required to remove 1 mole of electrons from 1 mole of atoms in their gaseous state. So I've got to remove 1 mole of electrons from that. That would involve moving that one away, moving that electron out. Okay, in this one here, I've got to remove 1 mole of electrons. Well, I could remove this electron here. Okay, so the fourth electron will get removed, and the reason it's easier to remove is that I've got 2 electrons next to each other here, so I have repulsion in that suborbital. Okay, so sulfur has a lower first ionisation energy than phosphorus because in sulfur the outermost electron is removed from a 3p4 subshell, and there is repulsion between the third and the fourth electrons, which makes it easier to remove the 1 mole of electrons. Okay, that's it for today. Thank you for watching. Don't forget to like and subscribe and click on the bell notification to keep you fully updated. Thank you.